So this video is going to be on the squeeze/sandwich theorem. They're two names for the same theorem. I usually use the name squeeze theorem, however, I'll probably end up going between the two within this video, but they both mean the same thing. And this theorem is a really useful theorem in calculus and real analysis for finding/proving the limit of a desired sequence. And the way it works is you squeeze/sandwich your sequence in between two other sequences that are both converging to the same limit, and you know that they're both converging to that limit, and then you can prove that your sequence also has to converge to that limit. So let's write this down. So we're going to have three sequences in total. We'll have a sequence AN, a sequence BN, and a sequence CN. And AN and CN are going to be the sequences that we know and understand. We know what they're converging to, and then BN is going to be our sequence of interest that we are trying to find what its limit is. And to say that they are sandwiching the sequence BN is to say that all the terms of the sequence BN are in between the corresponding terms of AN and CN. So if we draw a picture of this, so we have our sequence A here, A1, A2, A3, etc. We have our sequence B, B1, B2, B3, etc. We have our sequence C, C1, C2, C3, etc. And for every single number, 1 onwards, so all the natural numbers bar 0, it's going to be true that if you compare the first or the second or the third terms, this one is the smallest, this one is in the middle, and this one is the largest. So this holds true for all n is an element of the natural numbers bar 0. And of course, this is a simplification. This isn't quite necessary. It might be the case that for a finite number of terms out the front of the sequences, this doesn't hold true. What's going to need to occur, however, is that eventually this is going to be true. So hopefully you're aware, if you have a sequence and you cut off a finite number of terms, so let's just use the example of our A sequence. So let's say A is converging to some limit, and indeed for the squeeze theorem we're going to need that A is converging to a limit. So we'll have limit as n approaches infinity of AN is equal to some limit L. If you were to take away the first n-1 terms of this sequence, so cut away this starting bit of the sequence and then just consider the sequence going on from A big N onwards, that new sequence, that cut-off sequence, it's still a sequence. We're just going to renumber all the terms. So this is going to become our first term, the next one is going to be the second, etc. This sequence is still going to end up converging to the same thing. So cutting off a finite number of terms from the front doesn't change anything, because remember, it's what is happening to the infinite number of terms going this way that matters. And if the overall thing was getting and staying indefinitely close to this limit L, then once you cut away those finite number of terms, all of this will still be doing that. This will still have to be getting and staying indefinitely close to that limit L. So getting rid of a finite number of terms doesn't overall change what the tail end of the sequence is converging to. So actually, for this to apply, it doesn't necessarily have to be true for every element of the sequence, but it has to eventually be true. And this is a really important word that sounds as though we're just using it in the English context, but actually has a proper mathematical meaning. So when we say that this needs to eventually be true, it means that there has to be some point in the natural numbers. So there has to be some big N. So we might write this down. What this means, if a property is eventually true for a sequence, what it means is that there must exist a big N is an element of the natural numbers such that after that big N, so for all little n is greater than or equal to big N, that property holds true, that predicate holds true for the terms of the sequence. So I suppose formally we could write predicate P, meaning our property, holds true for an. So in this case, this is the property that we want to be true, this inequality. So it needs to eventually be true, i.e. there needs to be some big N. So I might put the other terms here, so B big N and C big N, such that for that term and or those terms and all the terms afterwards, this holds true. It doesn't matter if it's not true for a finite number at the start. However, for simplicity, we'll now just assume that our sequences from the beginning had this holding true. If it wasn't the case, then we can cut the fronts of them off. If it was eventually true, we can cut the fronts of them off and then just consider these new tail ends of the sequences as our sequence. But we'll just assume this from the start. And what I hope I've convinced you with this little discussion here is that if it's eventually true, i.e. if this holds true, then without loss of generality we can assume this, because we could always cut off the front ends of the sequence and just keep the tail ends, which are going to converge to the same thing. So let's now get on to the actual squeeze theorem then. So this is going to be true then, this inequality, and the important thing is that these two sequences, A and C, we're going to know what their limits are, and they're going to equal one another. So this limit L is also going to be the limit of the sequence Cn as n goes to infinity. So the statement of the squeeze theorem now is that if you have that this is true, that for all terms of the sequences this inequality holds true, and you know that the sequence A and the sequence C converge to a limit and that that limit is the same thing, then because this one is sandwiched in between these two, it now must also converge to that limit. So that's the result of the squeeze theorem. So the claim, and we'll prove this, is that the limit as n approaches infinity of our sequence Bn is also going to be that limit L. And the intuition, the picture for why this is happening, which we will turn into our proof, is that we have this limit L here, and we might have our sequence C coming from above and our sequence A coming from below. So here might be A1, here might be C1, and I might actually do them in colours. So we'll make the sequence A in blue and the sequence C in green. So here come the points A, the A points, so they're going to be converging in on this limit from below here, and the points of C might be coming in from above here so that the inequality is satisfied, so that all the points in A are smaller than those points in C. And then these B points, what colour should we do B in? We can do it in yellow. They have to be somewhere in between, so B1 is going to have to be somewhere in between, so it might be somewhere here, I don't know, because remember, it doesn't have to be in between all of the points of, it doesn't have to be bigger than all the blue points, it just has to be bigger than its corresponding, this is B1, so it has to be bigger than A1, and it has to be less than C1, so it could be here, for instance. And then they go on and on, so here might be some more of these B points, and they've always got to be sandwiched in between their corresponding point in the A and the C sequence, but that's obviously going to get narrower and narrower, that region that they can be in, because the points of A and the points of C are converging in on this limit L, and therefore it's going to be squashed in, and it's going to end up having to converge to L as well. That's kind of the intuition, and we're going to turn that into a rigorous proof now. So we want to prove this then from this fact and this fact here. So let's make some more space. So to prove the limit as n approaches infinity of Bn is equal to L, we need to apply the epsilon definition of the limit. So we need to show that the terms of that sequence get and stay indefinitely close to that limit L. So we'll take our closeness, epsilon, so let epsilon be greater than 0. So we've got our general epsilon, and we now want to show that there exists a big N such that for that term and all the terms afterwards, they are within that epsilon interval around L. So we'll draw our epsilon interval here around L. So this is L plus epsilon, and this is L minus epsilon. Now, the way we're going to do this is firstly by applying the fact that these converge to the limit L, and therefore we can apply the epsilon definition of their limits and say that there must be a point for both of these sequences where both of them are inside that epsilon ball around L. So let's do this. So I'll write because limit as n approaches infinity of an is equal to L. That means that there must exist a big N1 is an element of the natural numbers such that for all little n is greater than or equal to big N1, the distance between the terms and the limit L is less than epsilon, i.e. all of those terms from big N onwards are elements inside that epsilon interval around L. So we have a point, and I'll do this in blue. We have a point here. This is a big N1, which is inside that epsilon interval, and then all the terms beyond it, all the a little n, where little n is now bigger than or equal to m big N1, also are inside that interval. Now similarly, we're going to apply the fact that, not in blue, similarly we're going to apply in white the fact that the limit as n approaches infinity of Cn is equal to L, and say that there must exist a big N2 is an element of the natural numbers, and in general big N2 might not be the same as big N1, such that for all little n is greater than or equal to big N2, again the distance between the terms of the sequence and the limit L is going to be less than epsilon, but actually I'll write that in the more useful form to us, that those terms Cn are going to be elements inside that epsilon interval around L. So on our picture in green now, we might have our term here. This is C big N2, where it's inside that epsilon interval, and all the terms after it are also inside that epsilon interval. And now, of course, we're going to apply our inequality. We know that for all natural numbers, this is going to apply. So Bn has to be sandwiched in between An and the corresponding Cn term. The only problem we've got is that these two numbers aren't necessarily equal to one another, and hopefully you can predict exactly what we're going to do to rectify that. So our big N overall for our B sequence is going to be the maximum of big N1 and big N2. So one of these numbers is bigger. They might be the same. If they're the same, that's fine. We'll just make n equal to whatever number they both are. But in general, one of them is going to be bigger. Take that bigger one, and then if you go to that term of the sequence, so let's say, well actually we don't need to say, but for example, we could say big N1 maybe is the bigger one. So now we have this term a big N1, and then we could go to the equivalent term in C, so we could go to C big N1. So we've got a term even further along in the C sequence, C big N1 now. And if N2 was smaller than N1, which we just said, for example, we're going to assume, then this one is beyond it in the sequence. So just drawing a bit of that C sequence, C1, C2, all the way up to, here is C big N2. And we're now saying that big N1 was bigger, so big N1 will be over here. So that term's certainly beyond this one, so it's certainly going to be inside the epsilon interval, because all terms beyond big N2 were inside the epsilon interval. So everything beyond C big N1 is also going to be inside the epsilon interval. So now what we have is, if we also put the sequence A up here, A1, A2, all the way up to A big N1, we know that all of these terms of the A sequence are inside the epsilon interval, and all of these corresponding terms, the C sequence, are inside the epsilon interval. So that was an example assuming that the big N1 is bigger than the big N2. If big N2 was bigger than the big N1, then you'd do the mirror image example, where you'd go further along in the sequence A to the term A big N2. So in general, we can go to this big N, which is the maximum of big N1 and big N2, and we can then say that for all n is greater than or equal to big N, that the ANs are going to be elements of this epsilon interval, and also the CNs are going to be elements of the epsilon interval. So hopefully that is clear from what I've done here to explain that if you go to the maximum of this, then for all terms beyond that maximum, for both sequences, they're going to be inside the epsilon interval. So in particular, what we can say is that AN is going to be greater than, I just need a bit more space here because it's the little options menu is actually in the way. So it's going to be greater than L minus epsilon, and Cn is going to be less than L plus epsilon, and then sandwiched in between them is then going to be Bn because of the inequality that we know is true. So now what have we shown? Because for all little n is greater than or equal to big N, this applies. So this inequality is absolutely fine. It's true for all little n is greater than or equal to big N, and therefore we can certainly conclude from this, that all the Bn's are elements of that epsilon interval around big L. So there we go. We started with a general epsilon and we have found a big N such that for all the little n beyond that, Bn is inside that epsilon interval. All you need to do is go to these two sequences which we know converge to L, find the number of the term from beyond which all of their terms are inside the epsilon interval, and then just take the maximum of them, and that's the big N that you can use. And we've proven then that using that big N, from that term and all the terms onwards, this inequality must apply, and therefore all the terms of this sequence B must be inside there. And since we've done that for a general epsilon, it applies for all epsilon. So however indefinitely close you want to get to that limit L, I can find you a point in the sequence Bn where all of those terms beyond it are inside that closeness and stay inside that closeness forevermore. Hence we have shown the definition of convergence of B to L. So that's the squeeze theorem then. And you can do this for any, this L that these sequences are converging to. It could be anything. However, often the applications that I've used this in, and we do use it a lot, often it's the case that we want to prove the limit of our sequence is equal to 0, and often we're sandwiching it between two sequences that we know are going to equal 0. So just to give you a little bit more insight into that. So we might have some complicated sequence here, limit as n approaches infinity, of some complicated function which I'll call Bn. So now that's not subscripted Bn instead. This might be some complex function of n here. Not meaning complex as in complex numbers, just complicated as in it's something complicated. And we might know that this expression here is always greater than or equal to 0, for instance. So we know that it's always positive. And we might be able to show that it's always less than or equal to some other complicated function, c of n. And then we might sandwich it in between two sequences. One of the sequences is incredibly simple. It's just the sequence of 0, 0, 0, 0, the constant sequence 0, 0, 0, 0. And then we've sandwiched it between this other sequence, this C sequence. So if we can then show that this sequence converges to 0, then we'll have proven that this one is sandwiched in between those two and therefore must also converge to 0. That's the sort of application that I frequently see of the squeeze theorem. So it is an important, useful thing that we use to prove the limit of sequences in real analysis. So thank you for watching. We'll end there.